and let's move to the third paper of this session. It's called Digital Prototyping of a Microprocessor Control Active Knee Prosthesis. It's going to be presented by Guilherme. So share your screen, please, Guilherme.
Can you see? I'm changing now.
Yes.
So
yes.
Yeah, I'm going to present now. So hi everyone,
Okay.
My name is Guilherme.
Go
and
ahead.
As the chair said, you're listening, right? Yeah.
Yes, perfectly.
Okay. We were both saying at the same time, and I thought that you weren't listening. But as I was saying, my name is Guilherme, and I'm going to present the paper Digital Prototyping of a Microprocessor Controlled Active Knee Prosthesis. And this paper was produced in the Federal University of Espírito Santo in Brazil, alongside Pedro, Ulhoa, Antônio, Filho, and Rafhael, Andrade. In this presentation, I'm going to talk about the main topics of the paper as following the summary. First, I'm going to introduce the problem. Then I'm going to talk about the prototype itself and how we designed it. And then I'm going to talk about the modeling to verify the prosthesis, the capacity of the prosthesis, and talk about the conclusions. So first of all, we have to bear in mind the lower limb amputations problem, because they severely affect the amputees' biomechanics of locomoting in all daily activities, such as climbing stairs, walking on level ground, or in inclined planes, and sitting down, standing up. If you lose a part of your lower member, you're going to have a difficulty to do these movements autonomously. And because of that, lower limb prostheses are being used to help their upright ambulation and thus improve their quality of life, autonomy, and safety. Those prostheses can be classified into three types: the passive ones, semi-active, and active ones. But the passive ones will only aid the user to support himself and also inefficiently dissipate the energy that when you move, you have to produce energy, and also you have to dissipate it in order to make a stable movement. But the passive cannot do this active, to generate this active power, only dissipate them. And the semi-active ones, they only dissipate the energy, but they do it in a controlled way, which improves a little bit their quality of movement. But the active ones, they can produce and dissipate energy in a controlled way, and thus reproduce it more adequately the movement of the healthy leg, improving the user's mobility, independence, autonomy, and acceptance of the prosthesis itself. So the authors in this paper had the main goal to promote the rehabilitation of transfemoral amputees and knee articulation amputees by developing an active prosthesis that is compact, affordable, and lightweight, and simpler to control than other prostheses reported. So talking about the sizing of this actuator, for the basic design of the actuator and its structure, the knee range of motion and the maximum values of torque, speed, and power in the various daily activities were taken into account. And in this table in the right, as you can see, we have these requirements. And to get these values, we used an average subject from Brazil, which weighs approximately 72 kilograms. And we can see that for running, we have extremely high requirements for torque and power. So we dropped it as a goal to rehabilitate this activity. We only considered the other four. And to simplify the actuator design, we choose the motor reducer, a coaxial motor reducer that tries to balance these requirements presented, and it has to be lightweight and compact because the user cannot sometimes not tolerate something so heavy in the lower part of the body. So to that, we chose a 200 watts motor that was directly coupled to a 51-to-1 reduction harmonic drive that this pair weighs 0.53 kilograms and is capable of nominally reaching 27 Newton meters at 64 RPM, and considering an efficiency of 80% of the system, and it can reach peaks of 65 Newton meters for up to 5.5 seconds. I mix the buttons here. So for the digital prototype of the knee prosthesis, we took two steps. The first one, it was to draw 2D sketches to analyze, for example, the location of the bearings here in red, and also to see the connections part and between the parts, as can be seen from these lines here and this one, for example. And then we did the 3D prototype to design the slots and also to make the fabrication drawings of the prosthesis. And as a result, we have a range of motion of the prototype from 0 to 115 degrees of flexion, and a mass of 559 kilograms as a rigid actuator, but it can be used also as a series elastic actuator that increases its weight to 1.66 kilograms. The overall height between the pyramid adapter's extremities is 157.4 millimeters, with a maximum width of 112 millimeters, which shows adequate values in comparison to previous works. And also, all this structure here that we had to manufacture, it is made by 7075 T6 aluminum to maintain its resistance while reducing the weight of the prosthesis. And for the control part of the system, an Apple's compact 50/15 can powers the C60 flat motor that I talked about. That is that 200 watts motor, and the core control architecture is made in the BeagleBone Black Rev C that runs a MATLAB kernel, and the control algorithms are implemented in Simulink. And in the future, as we want to use the prosthesis in people, we had to develop a structure to connect the knee prosthesis to a foot. In this case, we are using a passive foot that is the Trias 1C30. And the overall mass of this prototype is 3.6 kilograms estimated by the software. Also, we estimated the gross cost to manufacture this first physical prototype at $9,000, which is significantly lower than the market price of the Power Knee, which is the only active prosthesis available on the market. And to access the capacity of the prosthesis, after prototyping the entire structure, we implemented the dynamic model and developed it by the equations 1 to 5 and implemented on a block diagram in Simulink. In this dynamic model, we use the properties of the virtual prototype and a torque disturbance that was derived from the healthy knee human gait that is responsible to verify whether the prosthesis would be able to supply the knee demand or not. And for that, when the power of the healthy knee is positive, the prosthesis has to supply the knee torque. So it has to provide this torque to propose the person propose forward the person. And when the healthy knee is dissipating energy, the prosthesis has to resist its external torque because it is a movement of dissipation of energy. And as a result, we evaluate the response of the dynamic model in 3 activities that were ground walk, stair ascent, and stair descent. And this was made with a movement at 3 kilometers per hour. And for that, we tuned a PD controller. As you can see on the graphs, for walking on the ground and climbing stair, the prosthesis shows good performance. But as for the activity of stair descent, the maximum torque that the prosthesis can deliver is saturated, and that generates this hyperflexion of the knee, and that this is a problem that we're now investigating, and we're seeking to minimize it in the future in further researches. So here in this presentation and in the paper, we showed an active knee prosthesis actuated by a motor reducer capable of supplying 60% of the maximum torque requirement, and also other requirements such as range of motion and to be low cost. And also we estimate that the prosthesis with the passive ankle should weigh 3.6 kilograms, which is a adequate value comparing to a healthy leg mass, and it can help the prosthesis user in all 3 activities, although it requires a greater care to descend stairs until now, while we are investigating the situation of the hyperflexion of the knee. And the next steps are to manufacture the prosthesis and to develop the prosthesis control software itself that will be responsible for generating the movement to the prosthesis, and then we will be capable to do tests on benches, on healthy subjects, and later on transfemoral amputees to validate the work that we did here. And finally, I would like to thank the Federal University of Espírito Santo and the Laboratory of Robotics and Biomechanics for granting me and Pedro Ulhoa our scientific initiation, and also to FAPS for partially financing this study. That's it. Thank you for watching.
Thank you very much, Guilherme, for your nice presentation. I think your work is really awesome. It's not too close to the things I do, so I think I mean it's quite complex for me to imagine all the steps and all the things needed to do such a thing. So congratulations and very nice presentation too. So I don't know if we have any questions. You may ask in the chat. When reading the paper, I was wondering about the software framework in which you run the simulations, but you actually say in the presentation that you use MATLAB and Simulink.
Yes.
I guess they are quite a standard for doing this kind of job, right?
Yeah, it's very common to use Simulink to model problems and to all kinds of problems, really. The Simulink has very numerous types of applications and features itself inside the software to model any kind of problem.
I see. And I was curious about any other kind of software for doing this kind of simulations. Did you ever use a framework in, let's say, in Python or something like that for this kind of work?
We didn't use it because it's a little bit more complicated, but we could use, I guess, but it's not my specialty. I'm not a programmer. I don't know the word itself, but
I see, yeah.
I'm not used to programming softwares or programs in general.
There are no tools prepared for doing that, like Simulink. No other options like that.
Including Simulink converts the code to C or other language in the software itself. So it's probably very plausible to do this in Python or other languages.
I see. Okay. I was also curious about the thing you mentioned, that when you did the simulations on stair descent, you had this problem, this discrepancy between simulation and the expected results. And so you mentioned that you were investigating on that. Do you have any clues on how to solve this issue, or could you comment on that?
Yeah, of course. We are seeking to modify the reference of the signal that the prosthesis is following, but when people is using it, probably the system will, as I said, in this case, it will dissipate only 60% of the maximum torque that healthy people would require. So probably the subject using the prosthesis would have to bear the part of the weight with the hand in the handrail that we see in the stairs or in the wall. But we can also try to, in the future, develop use, instead of this motor that we're using, a better motor that would be capable to produce more energy, but they are, until today, they are heavier or larger, and we wanted something more lightweight and compact. So this we did not consider, as we can tell the user to aid some kind of, to support some weight in the wall or on the handrail.
I see. Yeah. Okay, thank you.